Mesdames, Messieurs, chers collègues, prenez place parce qu'on va reprendre pour cette troisième journée du colloque Arctique, les grands enjeux scientifiques. Donc aujourd'hui, on a une session qui est bien pleine avec des thèmes, le thème climat, océan, glace, atmosphère, qui sera suivi du thème géodynamique et ressources naturelles, et ensuite cet après-midi du permafrost. Voilà, je vais donner la parole au chair de la journée. Marie-Noëlle Housset.
Bonjour, bienvenue à tous. Je suis Marie-Noëlle Housset du l'Océan, je suis océanographe et donc avec mes co-animateurs, nous avons en charge d'animer ce thème qui est un large thème et en fait qui représente, on l'a appelé climat, océan, glace, atmosphère parce que c'est un thème qui représente trois composantes d'un système Terre réduit, bien sûr, je ne voudrais pas fâcher mes collègues des autres thèmes, mais qui représente quand même le noyau de ce qui nous intéresse ici, c'est-à-dire la variabilité du climat dans l'Arctique. Et donc, ce sont des composantes qui interagissent beaucoup entre elles. Par définition, il y a un énorme jeu de rétroaction et de feedback qui sont mis en place, ce qui fait qu'on a voulu les mettre toutes les trois, ces trois composantes du système Terre dans le même thème, et ça devient du coup un gros thème. On a reçu une soixantaine de contributions orales et postères, dont nous n'avons malheureusement pu sélectionner que 4. Et puis, nous avons reçu une cinquantaine, un peu plus, de posts sur le forum. Donc, il y a là beaucoup de matière à travailler. Vous verrez que le rendu est encore très préliminaire cet après-midi. Et donc, nous allons tout de suite... on a donc choisi un exposé un petit peu dans chacune des composantes, et puis un exposé un petit peu plus global sur le système climatique couplé dans son ensemble. Donc nous allons commencer par la composante océanique et nous avons l'honneur aujourd'hui de recevoir donc le professeur Bert Rudels, qui est donc professeur à l'Institut météorologique de Finlande, à Helsinki. C'est un océanographe, je dirais, pur et dur, c'est-à-dire qu'il a fait toute sa vie dans l'océan Arctique. Il a fait beaucoup d'observations dans l'Arctique central, une dizaine de très longues campagnes, notamment une campagne qui a été très bénéfique, celle de l'Odène en 1991, qui a atteint le pôle depuis le Spitzberg. Et puis, donc, c'est quelqu'un qui observe beaucoup les masses d'eau, la circulation, et qui a élaboré un certain nombre de théories toujours très pertinentes et qui sont utilisées par toute la communauté sur le fonctionnement de l'océan Arctique. Donc, il va nous en dire là quelques mots, donc je lui laisse la parole. Et le titre de sa présentation, c'est « Le climat de l'océan Arctique ». Forçage radiatif local, transport de chaleur et eau douce. Ah oui, excusez-moi, je voulais aussi vous présenter mes co-animateurs, donc qui sont ici présents. Donc Chantal Clos et Frédéric Rémy. Frédéric plutôt pour les calottes et Chantal pour l'atmosphère. Et par ailleurs, le groupe comprenait aussi Catherine Ritz pour les calottes glaciaires, Valérie Masson-Delmotte pour les aspects paléoclimatiques, Catilo aussi pour l'atmosphère et Jean-Claude Gascard pour l'océan. Et enfin, David Salas-Imelias pour tout ce qui est modélisation du système couplé.
Thank you very much for the invitation here. Unfortunately, I cannot speak French, so you will have to have this presentation in English. And also, the title I have chosen, The Arctic Ocean Climate, the balance between local radiation and advected heat and freshwater. I hope that will become clear during the presentation why I've chosen this title. Oh. So, I mean, the question about an open Arctic Ocean isn't new for our time. In the 18th and 19th century, it was brought up the possibility to have an open ocean beyond the continental North America and Eurasia. And it was, for instance, Lomonosov was one person favoring it, Augustus Petermann in Germany, another one. And it might seem strange to have this view if you consider all the efforts that have been done to find the Northeast Passage, like let's see if we can find. Bard, he died on the Novaya Zemlya trying to get into the Kara Sea, and Franklin disappeared in the White here in the 19th century, and actually the expedition by Perry here penetrating almost through the Arctic archipelago into the Arctic Ocean when he had to stop in Winter Harbor to overwintering. And also the temperature and distribution of the Earth was well known at the surface, and beyond 70 degrees north, the temperature was below zero. So you would expect ice to freeze, or water to freeze, and you have ice. So what are the reasons to believing that you could have an open ocean? One was observations. The persistent polynyas exist north of the, for instance, Laptev Sea. Open water has been seen north of the Bering Strait. And there was a suggestion that maybe seawater cannot freeze because sea ice doesn't contain much salt. And then beyond the area where the influence of river water, you would then expect open water. And another feature was that the Gulf Stream would advect enough heat to keep the ocean open from prevent and keep the ice away by advecting heat up north. But in the 1984, the wreckage, part of the wreckage from Juliet was found in the Juliane Hope in 1984, and Jeanette had entered into the Arctic Ocean in 1879, so it's less than 4 years. The part of the ship has been advected through, and that gave Ansen the idea to penetrate into the Arctic Ocean by allowing himself to be frozen into the ice and drift to the ship. And he didn't find any open water in his track from the East Siberian islands into along the what would become the Nansen Basin, actually. What he did find was a deep ocean, and it was not to be expected, because if you have ice, you would expect shallow water, so you could remove enough heat to form ice. He also found that the Atlantic water was present there. It was warm above between 1 and 2 degrees, so the heat was really advected into the Arctic Ocean. The problem was that it was submerged under a low salinity surface layer, which increased the stability and prevented the heat from coming up and affect the ice. Actually, he also found that the high salinity deep water, those measurements are found to be wrong, but before he knew that, he suggested that there could be a deep water renewal inside the Arctic Ocean by the reaction of brines on the shells. And that has been later, they found that there's slightly higher salinities, and the reason for that is most likely brine reaction on the shells. In the same time, it was also believed that the meridional circulation was driven more by heat differences between the tropics and the Arctic Ocean. The Gulf Stream would be driven then by cooling, making dense water up north, which would sink down, and then return to the south. And Sandström in 1908 made an experiment, and he found out this kind of circulation. But he also found out that the circulation depending on the strength, and where you had the heat and the cold sources. If you have the cold sources above the heat sources, you get a strong circulation. If you have the reverse situation, you don't get anything, or at least he didn't observe anything. And of course, that is the problem which you all have to explain the thermohaline circulation. The heat and the cold sources are at the same level, so you need to have mixing to bring the heat down in the tropic. Another experiment was done by Nansen, published in 1912. He was adding ice on salt water and measuring the temperature. Actually, he did 3 types of experiment. He put the ice in a bowl on top of the water, and he got a rapid cooling and a convection. He put, like this experiment here, I'm a bit shaky, where they got above the sea surface, it was radiated cooling, and it was a slower but still a decrease in temperature. But if you put ice directly on top of the water, there was some slight cooling, and then it leveled out, no change in temperature here, some slight increase due to advection from the environment from the side. And the interpretation was that when ice is directly on top, it melts and creates a less saline water, which would prevent the heat from coming up and further melt the ice. So essentially, you have the most important processes which are controlling the Arctic Ocean, in the climate in the Arctic Ocean, were already known 100 years ago. You have cooling at a high latitude that makes warm water colder and denser, and it sinks down and returns. You have the fresh water on top of it, which stabilizes the water column and will prevent heat from coming up unless you have a strong mixing. And if ice melts and cools on top of the warmer water, it creates a less dense surface layer. The positive buoyancy by melting, adding fresh water, is larger than the cooling effect. So, and we then have a climate between the transport of heat, transport of fresh water, and the mixing processes, which then act to bring the heat up or not strong enough to do it. So the talk here, I will be trying to follow these lines. I'll talk something about early observations in the Arctic Ocean, then about the radiation and heat balance, about the circulation of Atlantic water in the Arctic Ocean, interaction with sea ice, freshwater balance and freshwater transport, and finally about the global thermohaline circulation. And early observations, and I mean the time before 1985, maybe, when you have not the large international expeditions. The enthusiasts that really went into the Arctic Ocean and disappeared for a couple of months. Like this expedition here, which was with a discarded submarine bought for $1. Nautilus, 1931, penetrating into the Arctic. They came up to Fram Strait, north of Fram Strait, and they found out they couldn't dive because the diving rudders were not functioning. I don't know if it's true, but there were rumors that some sensible person has sabotaged the rudders because he wanted to get back home again. And in any case, Sverdrup, one of the great oceanographers in the 20th century, he was on board and he also returned. He actually liked to observe from a submarine, and they got some hydrographic stations, and they managed by ballasting to get underneath to see that light penetrate underneath the ice. The more successful expedition was actually the Soviet Union's first establishment of the North Pole 1 station at the North Pole in 1937, and the ice camp was fairly rapidly and was picked up in the Greenland Sea in February 1938. And the Soviet Union continued with this airborne expeditions. There is the number of stations taken up to the 1950s, shown here, and planes on the North Pole. There were also ice stations which were drifting around, and several of these ice camps are being launched after the North Pole 1, most of them from the Soviet Union, some from Canada, some from the US. And that gave us our knowledge of the bathymetry, not as detailed as it is mapped from Martin Jacobson, but the Lomonosov Ridge was found, the deep Canada Basin, the Markov Basin, Nansen and Amundsen Basin, and the passage through Fram Strait. And they also did the drift of the ice and the surface current was observed at Bofoyaya, the transpolar drift, and the Siberian branch of the side. Transpolar drift bringing low salinity water from the shelf directly to Fram Strait. And blue, which is come out badly, is the maximum ice cover, and the red one, weak red, is the average minimum, and the dark blue was the 2007 minimum, which has been, now we have another minimum. So going to the radiation and heat balance, we know that most of the heat is coming at the equatorial region, less is heat in the region, the surface, the high latitude, but there you have a loss of heat, there's a deficit which has to be combined. You see here, in summer it's more or less balanced, in winter there's only heat going out. So you need to have heat being transported from the south, and that is mostly done by the atmosphere, but this heat transport doesn't really respond to the need for the heat loss to space. It's about the same magnitude in summer and winter, and part of this heat is then going into the sea surface, and here. This is there's a net heat transport to the sea, to the surface of the Arctic Ocean north of 70 degrees, which is about 5 watts per square meter. And but that is a difference between about a net of 35 watts per square meter long wave radiation and a loss, an incoming 39-40 watts per square meter from the shorter radiation annual mean. But the total incoming and outgoing long wave radiation are more between 300 and 400 watts. So it's a too large number, and the difference between, and then the difference between another two large numbers. But there is a heat loss at the surface, which is being evaporation and also by sensible heat, and that heat is more than incoming radiation, net radiation, and that is supplied by the ocean and as sensible heat and as ice export. And you can also see here that the ice has a double function. When you don't have any incoming solar radiation, you borrow heat by forming ice. And in summer, when you get more heat coming in, you melt the ice. And you don't melt all of it, part of it is being exported as ice. But if you only change the incoming long wave radiation, the downwelling from the clouds, by 1%, it would be enough then you wouldn't need to, you would melt all ice seasonally, and you wouldn't need to have this heat import by exporting cold ice. And actually the heat which is coming out by the ocean is only carried by the Atlantic, and that's the only ocean that really carry heat across the equator from the south to the north. And going into what that is supposed to do, we look at the circulation of Atlantic water. And one of my first step into the Arctic, by the way, was by the Ymer 80 expedition when we were studying the area north of the Barents Sea and in Fram Strait. The work in Fram Strait was motivated by the idea that the Soviet Union was planning to divert some of the rivers, one or two, entering into the Arctic Ocean to Central Asia for agricultural purpose, and would that limit the stratification, allow the heat from the Atlantic water come up and affect the ice cover. And the Fram Strait is where the warm Atlantic water enters. This is where the low salinity surface water comes out, and that's also part where colder Atlantic water is leaving. In this range here, where you have a circulating temperature, salinity between the temperature of plus minus 0.5 degrees, it's very wide range in the outflowing area here. It's very narrow when it's coming in, so that is the colder Atlantic water coming back out. Further into the basin, 10 years later with Rudels, we found that the strong fronts in the Eurasian basin, one front more or less located over the Gackel Ridge, another over the Lomonosov Ridge, indicating that the temperature the high temperature remains in the Eurasian basin. And that was further proven by expeditions from Polarstern, being taken further closer to the Laptev Sea, where you see a low salinity and colder inflow originating from the Kara Sea, the water entering over the Barents Sea actually. And that seems to take over the transport into the other part of the Arctic Ocean, while the heat from Fram Strait remains in the Nansen Basin mainly, as you can see here. So making a cartoon of it, you have two inflow coming in here over the Barents Sea or Fram Strait. The warm inflow here, has lost most of the heat over the Barents Sea, and it stays in the but it supplies most of the Arctic Ocean. At least that's my view about it. It can be argued. When the Atlantic water meets the ice, it starts to melt, like the Nansen experiment, and you create a low salinity, colder layer, which is gradually deepening and melting more, so you're increasing the buoyancy by adding fresh water at the same time as cooling it. And since the heat's coming from below, the stratification depends on how much of the heat from the ocean is actually going to ice melt and how much is just disappearing to the atmosphere. And you can compute how there's a fraction where they have the minimum ice melt, which is more or less 30%. It's given by a formula. It takes into account the heat expansion of water and heat capacity and the latent heat. And then you can, when you reach the sea surface or the upper layer reaches the freezing point, you can compute the salinity, this is a temperature salinity diagram. Those who don't know how much what that implies is that you plot in each station, you plot temperature versus salinity, and as you go down. These are densities. You can think about this as depth. And so this is the summer melting. In winter, you have a mixed layer at a point here, and this is the lower Atlantic layer. And this is where we end up. The salinity, if you use an expression like this, if you take all the heat lost going to ice melt, you get these points here. They're a bit off. So it seems like not all heat is used for ice melt, only a fraction of that. And so the Atlantic water comes in, and here you create an upper low salinity surface layer, and that is being, every winter you start freezing ice, removing the meltwater layer, ventilating down to the Atlantic layer. From the Laptev Sea, you get an inflow of low salinity shelf water, and here you get inflow of low salinity Pacific water, which covers this originally low salinity layer. Still there's salinity, and they become isolated, and everything is then exported out of the Arctic Ocean. And that brings us directly then to the freshwater balance and the freshwater transports. And there you have freshwater. It's transported by the atmosphere. It rains on continent, and to get the river runoff, it rains directly onto the Arctic Ocean. You have a low salinity inflow from the Bering Strait, supplying fresh water, and all this is coming out in the North Atlantic, mainly as liquid water, fresh water through Canadian Archipelago, and also in the East Greenland Current in Fram Strait, and then you have the ice export. And that is controlled mainly by the wind, and I will not discuss that presently. It's more about the freshwater export as liquid freshwater. And if you're in cold water, density is mostly controlled by salinity. And if you have your strophic flow, essentially it's a balance between the slope of the sea surface and the Coriolis force in the upper layer. In the lower layer, it's assumed to be at rest. Then you can find out that the amount of freshwater exported only depends upon the thickness of the freshwater layer in this wedge traveling out, and the number of coast which this wedge can lean on, and the salinity of the lower layer. And they essentially have three openings: Lancaster Sound and Ayr Strait in the Canadian archipelago, and Fram Strait entering into the Greenland Sea. So if you have the freshwater export, runoff, net precipitation, Bering Strait inflow minus the ice export, then you can compute backwards and find out how much freshwater what is the freshwater layer thickness in the Arctic Ocean, and you end up with something like 8.5 meters, which is more or less, if you flatten this one out, is more or less what you find out. If you would melt or no ice was exported, you would add another amount of Sverup's, 1 million cubic meters per second exported, then you would need 10 meters to export all the fresh water which is added. And essentially the storage increases as the freshwater export square root, and the residence time increases as 1 over freshwater export square root of that. And that is independent of the mixing mechanism. But as you see, the mixed layer is not uniform through the deep Arctic Ocean. It means that, and here I've assumed that the thickness at the passages is the same as the mean thickness here. That is not. And if you change that, of course, you will get another value. And these disturbances are caused by the wind field, like circulation patterns, like the Arctic Oscillation, North Atlantic Oscillation, and that will then add and detract from this transport. But the hope would be that you can, just looking at the freshwater export, you could find a mean, and this would be annual to decadal variability upon that mean. Going into the global thermohaline circulation, there's an educated thing about Stommel's two-box model. Actually had 2 boxes, and determining the temperature and salinity in each boxes by mixing. And if you cool this one or when you add fresh water, but this one becomes denser, it will press down, this one in following them. It will fall down, and you will have a flow here. That will lower the sea level. You will have a return flow into the boxes, and you get the circulation. And since heat and salt is diffusing differently fast, then you can get a situation where with several solutions, you can have one cold solution where you have the fresh water is dominating, and you can have 3 solutions, 2 stable one, where you have the heat is dominating. Another perhaps clearer way to think about this, you have a thermally driven circulation. Warm water is moving north, being cooled and sinks down. You have a circulation like this. If you have evaporation and here increasing the salinity, you really have to mix water up here to get the circulation. So that would be less efficient than this one, where you really are at the forcing, like in the Sandstone experiment. Another way to look at it, if you have a perturbation, you have a symmetric flow and you have a perturbation. If warmer water is coming up here, you will get more heat radiated out, and the disturbance will be removed. But there's no way you can remove it. So you get more saline water here. There's nothing that the atmosphere, it doesn't care about if it's more saline or not, at least not from below. And then you can get a situation where you have a breakdown from a symmetric circulation in each basin, like you have a sinking in the North Atlantic, and in the Pacific you have a perturbation in the other direction, and eventually you get the circulation over the whole globe. And that is what we actually observe. We have the fresh water being exported from the North Atlantic into the Pacific, increasing the salinity here, generating more dense water and a thermohaline circulation. Here you have low salinity water, part of it is being forced back through Bering Strait, and then adding the low salinity water and the fresh water which we had before. And so this is the part which we normally consider about the thermohaline circulation, driven by the sources here and also here on the Antarctica. And still you need a mixing, you need to get the water up again. So that's the argument is out of cooling, densification, the forcing, or is the mixing, bring it back again, what controls how fast this works. You also have to think about that the wind-driven circulation is also carrying heat. It doesn't cool as much, but it's much larger in volume, and it can supply 40% even in the North Atlantic, more like that in the other oceans. But the part where you really encounter the storm type of model is a picture like this. We are here somewhere, there's a freshwater being added in the northern part of in the North Atlantic. If you add more fresh water, it will gradually move into this point, and then you will fall off the cliff and enter here, and then you are in the freshwater-driven mode of circulation, and then you really have to decrease the freshwater input to get back into the warm mode. But of course, this is a simple model. Can you really trust what it's saying? But what we can see, the effect of it is here you have the warm water coming in, always at the surface, adding heat, and then eventually being cool enough to sink down. During the glacial period, there was an event, you could be jumping back and forth like the Darsker events, or you have the Heinrich event where you're really flooded by ice from the glaciers, and then you got into this part here. But if you compare it wasn't supposed to look like this. The last glacial maximum, we have much more ice on land. It was lower temperatures, it was higher albedo, less outgoing long-wave radiation, less incoming short-wave radiation, and you could maintain the energy balance, but actually exporting ice into here, so you allow it to melt here. So the freshwater transport is supplying the heat balance mainly by exporting ice, which melts here in the warmer part. The situation today is a bit different because the atmosphere provides most of the heat in meteorological heat transport, and part of that is through the condensation of water vapor, which also affect the radiation balance. And if that continues, you would not need to have an ice export to close the heat balance, and then you could be into the situation of a seasonal ice cover. And the transport of oceanic sensible heat could become smaller once because you are lowering the heat forcing by cooling and also by increased the fresh water. But that would mainly be increased a stronger hydrological cycle. But on the other hand, if you start adding ice from Greenland, melting ice from Greenland, then you could get more fresh water, and we are into the unknowns. But to my non-expert opinion, that the Arctic today is mainly controlled by processes occurring in low latitude, and especially then the meridional transport with water vapor, because it affects the heat balance, and it also affects the radiation balance. And as I said, 1% more incoming long-wave radiations would be enough to say that we don't need to export ice to keep the heat balance, if you can think that simplified about things. And just to open the ocean, some open questions, which there is why and how does the Atlantic water lose its heat? North, you have the melt part when it melts ice, then it forms a low salinity upper layer. But beyond that, since it's coming down cooler, how does that work? Is it by mixing with the Barents Sea branch, or is it actually that you can get heat through the mixed layer, through the ice, without really adding to that you prevent ice from forming by giving the atmosphere heat being mixed from the Atlantic water without this melt part? And how much would that then reduce the sea ice production in the Nansen Basin, where the Fram Strait inflow actually occurs? And another thing is that why would a fraction of oceanic heat giving minimum ice melt it looks like it can predict the salinity of the upper layer, but why is that so? I mean, why should it be minimum? I mean, we are used to minimum principles in mechanics, but it's not necessarily so that it should be valid also in the ocean. And how well can you describe them in freshwater export by a simple geostrophic flow through the passages? I mean, you saw the wind fields would really change the thickness and bring fresh water to the passages, remove them, and that might be a more dominating part. I personally think that this is a valid first zero-order assumption. And then you have what drives the Atlantic inflow. Is it a large-scale wind field balanced with wind stress curl, removing the curl by friction on the geostrophical contours, or is the water transforming, which is transforming the Atlantic water, forming it in? And the follow-up of that one is, if you have an increased flow forced by wind, bringing more heat into the Arctic Ocean, can the Arctic Ocean take up that heat and deliver it to the Arctic as a whole, or will the Atlantic water come back warmer than it normally would be? And so then it would be determined by the mixing processes. And another one, the opening and the closing of the Bering Strait. So most of the ice in the glacial times are located on the American continent. So it doesn't say how the ice actually starts, but when you close the Bering Strait, the fresh water which is being advected by the winds over the Isthmus of Panama would then perhaps land on the North American continent. On the other hand, when you have the melting and you open the Bering Strait, it would be more easy to empty a channel from ice and change the climate than if you have a bay, which you have North Atlantic Bay if you have the Bering Strait closed. Yes, thank you.